Do we have theorems that we can use? We definitely do. And we should use them because sometimes solving the dependence equation can be a real pain in the backside. So you have a vector space V. If that vector space has a non-zero vector V, then the set of that one vector is linearly independent. If you look at the set of the zero vector, then it's not linearly independent. The only way for a set of one vector to be LE is if the vector is not the zero vector. So in an if and only if statement, there are two things we need to show. We need to show that the first bit here implies the second bit, and we also need to show that the second bit implies the first bit. So in an if and only if statement, two things to show. Well, let's start with the end. If the vector is not the zero vector, then if you look at the dependence equation, so if you look at a linear combination of all the vectors in the set, because there's only one, it's going to look like kv is equal to 0, and that only has one solution. It's when k is equal to 0. So you certainly have linear independence. So if v is not equal to 0, then the set that only contains v is linearly independent. Now we need to show the second implication, which is to say that if you start with a set that contains one vector only and is linearly independent, then we got to show that v is not equal to 0. When you show an if and only if statement, you're actually trying to show a statement that looks like this. That notation says that you have to show the implication in both directions. So that's the same thing as A implies B and B implies A. But there's a thing about these implications. A implies B is not in general the same thing as B implies A. But it is going to be equal to not B implies not A. In mathematical logic, A implies B is an implication. B implies A is the converse of A implies B. It may or may not be true, depending on the situation. Not B implies not A. This is called a contrapositive. The contrapositive is always the same thing as the original implication. It's just another way to see the situation. So if A, for instance, was the statement, it is rainy outside, and B is the statement, it is cloudy outside, or there are clouds in the sky, then A implies B says, if it is rainy outside, then there are clouds in the sky. That statement we may assume to be true. The converse of that statement would be, if there are clouds in the sky, then it is rainy. And we know that's not true. It is very often overcast without raining. The contrapositive of that statement would be, if there are no clouds in the sky, then it is not raining. That's true. That's the same statement as, if it is raining outside, there are clouds in the sky. So for the second part of the proof of that theorem, instead of proving that if a set with only one vector is linearly independent, it has to be that v is different from 0, we are going to prove the contrapositive. If the conclusion is negated. So if V is equal to 0, then we're going to show that the set V is not linearly independent, or in other words, that it is linearly dependent. Well, it's going to be linearly dependent if it has a non-trivial solution to the dependence equation. And it does, right? Because if V is equal to 0, the dependence equation looks like K times V is equal to 0, and you could pick K is equal to 3. 3 times 0 is 0. And so you have a non-trivial solution to the dependence equation. I spent more time than I wanted to on this proof only because I explained to you why there's two things we're proving, first of all, and why we prove the second implication using the contrapositive. It's a very easy theorem to prove, but you need to know what it means to prove things. So make sure you understand that in an if and only if statement, which we also call a biconditional statement, you have two implications to prove. And when you try to prove an implication, you can go and prove it directly, which is what we did for one of them. But sometimes an implication is more easily proved when we go through the contrapositive. Not B implies not A. Be careful, the contrapositive is not the same thing as the converse. This is an instance here where the converse and the statement are equivalent, but that's not usually the case. Most theorems are just implications. Think back to the rain and cloudy skies example. If you have a set of vectors which is linearly dependent, then any set that contains these vectors is also linearly dependent. Now, because the set is linearly dependent, there is a non-trivial dependence relation, right? I mean, you can write a linear combination of the m vectors being equal to 0, and one of the solutions has at least one of the coefficients being different from 0. Now, let's say that you have a bigger set that at the very least contains the m vectors that we know are linearly dependent. Then you can set up a dependence equation that would look like a1v1 plus a2v2 plus amvm for sure, and then with these new vectors 0u1 plus 0u2 all the way up to 0uk. Set that equal to 0. Now that's a dependence equation. And you know that that's a dependence equation with a non-trivial solution because not all of the coefficients are 0. Sure, there's a bunch of them that are 0, but there's at least one of the AIs here that wasn't 0 because we assumed that the first m vectors were linearly dependent. So the big set is also linearly dependent. If you have m vectors that are linearly independent, then any subset of those has to be linearly independent as well. So if you have a bunch of vectors that are linearly dependent, adding more vectors to this doesn't change the fact that they're linearly dependent. And if you have a set which is linearly independent, taking fewer vectors doesn't change that fact. I'm about to prove that for you in a second. But if you have a set which is linearly independent and you add vectors to it, you might change the nature of the set. And similarly, if you have a set which is linearly dependent and you remove vectors from that set, you may change the nature of the set. In fact, the two theorems are really the same theorem, right? When we say here that any linearly dependent set is such that any set containing that linearly dependent set is also LD, we have a statement of the form if A, so this part here is A, then B. So this theorem is really A implies B. What I've told you, know this from mathematical logic, if that A implies B, if that's true, then not B implies not A. The contrapositive is also true. They're equivalent statements. Well, what would not B implies not A look like? It would look like if it is not the case that any set containing V1 to Vm is linearly dependent, then not A, V1 to Vm is not linearly dependent. That's exactly the same statement as the statement which is right here. I'll let you look at this. As a corollary, the set that contains only the zero vector is linearly dependent, and that's something you get directly from the first theorem. So any set that contains the zero vector, because the zero vector is linearly dependent as a singleton, must be linearly dependent. So, I mean, if I was in the mood to ask you a trick question, if the zero vector is in your set, the set has to be linearly dependent. Another result of that, another corollary, if you want, is that if you have a set of two vectors, that set is going to be linearly dependent if and only if U is a multiple of V. So there are two things to show here because this is an if and only if statement. A set of two vectors is linearly dependent, then you want to show that U is a multiple of V. Yeah. And the second thing you want to show is that if U is a multiple of V, then the set is linearly dependent. So two things to prove, and typically you'll use a word like conversely here to let people know that you're about to start the second half of the proof in the other direction. So let's assume that the set is linearly dependent. Then you can set up a dependence equation, AU plus BV is equal to 0, which will have a non-trivial solution. So at least one of A or B is non-zero, and we have AU plus BV is equal to 0. Let's say that it was the A that was not 0. Well, if A is not 0, then I can divide this equation here by A, both on the left and on the right. If I divide on the left, I get A times U divided by A. That gives me A divided by A, which is 1. So U plus B times V divided by A should be equal to 0 divided by A. But 0 divided by anything gives me A. I can do these divisions here because A is a scalar and it's not 0. That makes sense. And if U plus BV divided by A is equal to 0, then I can send this thing to the other side. So I have that U is equal to minus B over A divided by B. I don't know what B and A actually are. The only thing that I know for a fact is that A is not equal to 0. But given this relationship between U and V, what I can see is that V is a multiple of U. I've multiplied V by some quantity to get U, or U by some other quantity to get V. So they're multiples of one another. You say, well, okay, you told us, assume that A is not equal to 0, because at least one of those had to be different from 0. But what if A was equal to 0? If A is equal to 0, then I can't do that. But if A is equal to 0, I know that B cannot be equal to 0, because otherwise A and B would both be equal to 0, and that wouldn't be a non-trivial dependent solution anymore. That would be the trivial solution. So if A is equal to 0, if A is different from 0, then I've shown what I wanted to show. If A was in fact equal to 0, then all right, but B cannot be equal to 0, and then you work through the same argument, and you can show that V is equal to minus A over B times U. And so that V and U are U is a multiple of V as well. Okay, so that proves it, forgive me, proves it in one direction. In the other direction, let's assume that u is a multiple of v. Or, so perhaps u is equal to c times v, or you can write v as c times u. These are saying the same things. It's not the same c. I mean, this c here could be a different c, but the point is that you can write u as some scalar times v, or v as some scalar times u. The c that shows up here would be 1 over c for the c that shows up here. Let's stick to the first description of u and v. If that's the case, then I can take CV and send it to the other side. So I have u minus CV is equal to 0, and that here should really be a 0 with a norm, or with an arrow on it, or like a bold 0. So what this is telling me is that what I have here is a dependence equation for u and v. And notice right here, the coefficient is 1. 1 is not 0. So this dependence equation is non-trivial. And so the set is linear dependent. Be careful though. This is interesting or important only if you have 2 vectors to start with. If you have more than 2 vectors, if you have 3 or more, then it's possible that a set is linearly dependent, LD, even though pair by pair, no 2 vectors are multiples of one another. 1, 0, 0, 1, 1, 1. That's linearly dependent. We've shown it before. But 1, 0 is not a multiple of 0, 1. It's not a multiple of 1, 1. And 0, 1 is not a multiple of 1, 1 either. So this result about being a multiple of another vector only is useful in the case where we start with 2 vectors. A set of m vectors is linearly dependent if and only if you can find at least one vector in the set which you can write as a linear combination of the other vectors. Or in other words, if there's one vector in the set, let's say vk, which is in the span of all of the other vectors. Again, there are 2 statements here to prove, right? You go in one direction. If this set is linearly dependent, then there's at least one vector vk in the set, which you can write as being in the span of the other vectors. And then there's the other direction. If there is at least one vector in the set with that vector in the span of the other vectors, then the full set is linearly dependent. 2 things to prove. We're going to start by proving the first statement, where we suppose that first bit is valid. We suppose that the m vectors are indeed linearly dependent. Then you can find a non-trivial dependence relation, a1 v1 plus a2 v2 all the way up to am vm is equal to the 0 vector, and at least one of those coefficient is different from 0. They're not all equal to 0. We'll say that it's the first one that's different from 0. Worst case scenario, if it wasn't the first one, all we would do is relabel or renumber the original vector so that whichever one at least was not 0, we can just say it was v1. That's what happens here. So the name we give them, the label we give them, is not important. If that's the case, if a1 is not equal to 0, then you can take the original relation here and divide everything by a1. So you get v1 plus a2 over a1 v2 plus all the way up to the last one, am over a1 vm is equal to 0 over a1, but 0 over a1 is just 0. And then I take all of the other terms apart from the V1 and I just send them to the other side. So I subtract them. And I end up with this. V1 can be written as minus A2A1 times V2 minus all the way up to minus AM A1 times VM. Well, that's a linear combination of the vectors V2, V3, V4 all the way up to Vm, and so V1 is indeed in the span of the other vectors. So if you start with a set of vectors, M vectors, which are linearly dependent, then you can definitely write one of them as a linear combination of the other ones. So one vector is at least in the span of the other vectors. In the other direction, let's assume that, we'll take the last one here, we could rename them or renumber them if we must, but let's assume that the Vm is that one vector which is in the span of the other ones. Then, if that's the case, Vm can be written as a linear combination of V1, V2 all the way up to Vm minus 1. And then I can just send Vm to this side here, subtracting on both sides. And that gives me a linear combination of the m vectors, which is equal to 0. In my construction here, the coefficient is minus 1, which is different from 0. And so this linear combination is non-trivial, and it adds up to 0. And so the vectors v1, v2, v3, all the way up to vm, not vm minus 1, are linearly dependent. And that completes the proof. We proved both directions. Might not be clear to you that this is something you need to do, but if you're asked to demonstrate that an if and only if statement is true, you have two things to prove in general. One direction and the other direction. Make sure you understand the distinction between these two directions. Now, let's be careful. Let's look at the statement of the theorem again. It says, there is at least one vector which is in the span of the others. That is not saying that every vector is in the span of the remaining vectors. There's just at least one which is in the span of the others, right? I mean, if you look at the set 1, 0, 0, 1, and 0, 2, that's a linearly dependent set because you can write a non-trivial dependence relation. 0 times 1, 0 plus 2 times 0, 1 plus minus 1, 0, 2 is exactly the 0 vector 0, 0. And some of these coefficients are not 0, like 2 and minus 1, they're not 0. So the set of these three vectors is linearly dependent, forgive me, but the first vector at 1, 0 is not in the span of the remaining ones. What the theorem tells us is that since this set is linearly dependent, there is at least one vector which is in the span of the other ones. For instance, the vector 0, 2 is in the span of 1, 0 and 0, 1. Just we don't know that this applies to every single one of the vectors because 1, 0 is not in the span of 0, 1, 0, 2. Span of 0, 1, 0, 2 is a line, and it's the line that is parallel to the y-axis. 1, 0 is not in that line or on that line. But 0, 2 is in the span of 1, 0, 0, 1. Right? So at least one doesn't mean every vector.